Добрый день. Меня зовут Fernando Gon. I is Argentinian. Моя презентация is Ipv6 security. How did we get there? Извините, не знаю больше русских слов. That's all my Russian. So I spend more time practicing the 3 lines of Russian than the rest of the slides, I should say. Hopefully you got the message. This presentation is going to be about Ipv6 security. The title is Ipv6 security. How did we get there? Here. As a kind of brief presentation about myself, I work for a company called Ipv6 Networks. It's based in Argentina. For the last 10 years or something, I've been working in communications protocol security. I have been involved in protocol standardization, particularly at the IETF, but in other standards organizations too. As part of that work, I authored about 30 RFCs, around 10 of which have to do with Ipv6, and they were mostly security patches, if you want, for the Ipv6 protocol. I have also worked in an Ipv6 security toolkit, and part of the work that I did on communications protocol security was for these 2 organizations from the United Kingdom. And at the end of this slide, you have a link to my personal website where you can find articles, publications, documents, and so on. Goals of this presentation, what I will try to do as part of the presentation. First of all, try to help you understand the security implications of Ipv6. Also provide some hints when it comes to how to exploit some of the security issues that we will be discussing, and also how to mitigate them. And I will also try to walk you through some of the design decisions behind Ipv6. So there will be some aspects of the protocols that maybe you are wondering, well, why are things the way they are? And I will try to provide some background, for which the things are in the way they are. You should have in mind that obviously Ipv6, as most other protocols, they are developed by standards organizations. So even if you might assume that, for every aspect of the protocol there is a technical reason, obviously there are some politics, if you want, some committee decisions. So, when some aspect of the protocol has to do more with that than with, a technical decision, I will try to make it clear. As a side comment, even when there is like a section for questions, if during the presentation you have some question, please raise your hand and you can ask the question. That also, I guess, makes the presentation more interactive and more interesting. And also, in the same way, if for some reason you disagree with something that I said, it's also okay that if you raise the hand and you provide, let's say, an alternative view about any of this topic, it's 100% okay. Okay. So, obviously, when I was, preparing the contents of this presentation, there was a lot of material that I could possibly include here. In my case, I have spent like many years on Ipv6 security itself, so I tried to include in this presentation those topics that, in a sense, are understandable even by somebody that hasn't spent a lot of time on Ipv6. Okay, so the idea is to go through the main security aspects of Ipv6, and even if you haven't spent that much time on Ipv6, you should be able to understand the main security implications. The idea is that you can take home something out of this presentation, as opposed to just getting into very small details and go through a presentation that you say, well, maybe what he said is true, but I don't understand, or I didn't get what it was about. So first topic is Ipv6 addressing. As you probably know, the increased address space of Ipv6 is the main driver for v6 deployment. Actually, it's the only driver. There's a lot of marketing around Ipv6, so you might hear things like, Ipv6 has improved security, improved quality of service, and so on, which is not true, obviously. So the only driver for v6 deployment is the increased address space. We ran out of IPv4 addresses, we need something with more addresses, and the only thing that we have on the table for that is IPv6. That's it. IPv6 employs 128-bit addresses. When it comes to the addresses themselves, the semantics are the same or very, very similar than those of IPv4 addresses. For example, for the purpose of routing, the addresses are aggregated into prefixes. We have different address types like, unicast, multicast, and so on. There are different address scopes. That's the same thing as in IPv4. You can have some sort of local addresses, some sort of global addresses, and so on. That's the same thing. Probably the only difference, or the only main difference in this respect, is that in the typical case in IPv4, every network interface card gets a single IPv4 address, okay? Whether that's a public address, whether that's a private address, but you typically get only one address. Whereas in the case of IPv6, every interface card usually gets at least two addresses. One link local address and usually some global unicast address. So that's the only difference. And that's something that, people that are new to the protocol, sometimes they check the configuration of the network interface cards and they wonder, well, how come that I have multiple addresses? Well, that's IPv6 by design. Every interface card usually has more than one IPv6 address. Let's discuss a little bit the syntax of global unicast addresses. Obviously, there are different address types, as I mentioned before, different address scopes. But as you might imagine, the global unicast addresses are the addresses that you'd use, for example, to communicate with a public server. If there was some web server, mail server on the internet, these are the addresses that you would employ. If you look at the syntax of IPv6 addresses, you see that there is a global routing prefix, some bits for subnetting, and an interface ID. And obviously, if you have ever seen an IPv4 address, you will realize that this is quite similar to IPv4. You have a global routing prefix, some bits for subnetting, and also in the case of before, you have host ID. Well, in IPv6, it's just called interface ID, but it's exactly the same. Obviously, the only thing that changes is the size. So, for example, in the case of before, the host ID might be like 8 bits, whereas in the case of IPv6, it's typically 64 bits. But that's the only difference. The global routing prefix is typically assigned by your ISP, okay? It's a prefix that is delegated. The subnet bits is the bits that you use in your network to segment your network into multiple subnets. And the interface ID, in principle, just has to be a number that results in a unique address. So it doesn't really matter what you put there as long as the result is a unique address. Same thing as IPv4. It's not important what you put in the host ID. It's not really important. You just want to get a unique address. Obviously, in the case of IPv6, the interface ID is quite large. It's 64 bits. So there are many options when it comes to what you can put in there. So here I have mentioned some of them. For example, in the first bullet, you see the modify EUI64. That's a complex or formal name for saying put your MAC address in the interface ID. Okay? That's like one way of generating an IPv6 address. Then there are other possibilities. For example, this one, which is temporary addresses. There are stable and random addresses defined in RFC 7217. You can have manually configured addresses and others. But for the purpose of this discussion, we're going to focus on the IPv6 addresses that are generated by including the MAC address in the interface ID, okay? Before we actually get into the details, I'd like to comment on two aspects because this is kind of like going to be useful for some of the discussion that we will have later. The first thing that you might wonder is why 128? Why? Is there anything special about this number? Well, on one hand, you might say that, multiples of 8, 32, or 64, is usually what you usually employ because they are, it's numbers, they are lengths that can be processed with good performance if you want. But the reason for which we got to this specific number of 128 is because it was a decision by a committee, a standardizations group. Essentially, at the time when the IETF was trying to design a protocol that would be the successor of IPv4, there were a number of competing proposals. These are some of the proposals. There were many more, like Tuba and CAPS, SIP, PIP, and others. Some of these proposals, for example, they were employing 64-bit addresses and fixed-length addresses. For example, a fixed-length address of 64 bits. There were other proposals like Tuba here. They were employing variable-length addresses of up to 160 bits. So eventually, among all the competing proposals, well, the IETF had to come up with something, and they got to a compromise of 128. That was the number that made the different people that were there happy, if you want. So that's the only magic about this number. So there's not like a technical reason for the specific value 128. It was like a compromise between different proposals. Then, if you look at the size of the host ID, nowadays is 64 bits. So that means that whenever you have an IPv6 network, the prefix length is going to be a /64, no smaller than that. And you might wonder, well, why do we have? Well, first of all, why we have such a limit? Why can't we have something like in IPv4 where I can use as many bits as I want, for example? Or besides that, why did we agree on the specific number 64? Why not 48 or why not something else? Well, the reason for which there is an artificial limit that was introduced for the host ID part in IPv6 is because the designers of the protocol wanted to avoid what is usually referred to as the run to the bottom. Let's imagine this. If you allow ISPs to give you as many addresses as they want, it would be very likely that they decide to give you a single address. So we would end up in the same thing. So the ISP gives you just a single address, and if you want to connect many systems to your network, you'd probably end up using NAT again, okay? Obviously, the whole point, or one of the reasons for going through the effort of deploying IPv6 was to avoid at least the need or the requirement to do NAT. So that's why this limit was introduced. So the designers wanted that it wasn't possible for an ISP to give you less or fewer than a /64. That's the reason for the limit. And if you wonder why /64 and not maybe /48 or a different value, actually, that's a good question, because at some point in time, the IPv6 subnet size was a /48, okay? But many years ago, like maybe 20 or something, there was this technology called Firewire, you might remember, and this technology was employing 64-bit link layer addresses, okay? So what the IPv6 designers wanted was that the interface ID part could actually accommodate the entire Firewire address. Okay? Obviously, if you think about that, from today's point of view, that's kind of like wasn't that nice because nowadays, at least that I know, nobody uses Firewire. But the reason for the /64 was to accommodate for 64-bit link layer addresses. So I made these two comments because usually, when we start discussing IPv6, people assume that, yeah, the addresses are 128 and, the subnets are /64, but it's never clear, why. And, in some of the discussions that we will have later, we will see that this has an implication on a few things. So, first of all, we will start discussing what is called the traditional SLAC addresses. So in the case of IPv6, the mandatory mechanism for configuring addresses is not DHCP, as in the IPv4 world, but it's something called SLAC, okay? The idea, obviously, there are details in there, but the idea is quite simple. Whenever you connect a host to a network, your host is going to ask the network what's the prefix that should be used for that network. And so some local router will tell your host, okay, you have to use this /64. And once you know the prefix, well, you have to come up with a unique address. So you have the prefix, and now you have to select something for the interface ID. Obviously, from a point of view of interoperability, the only thing that matters is that the number is unique. That's the only thing that is important. So the question is, well, how do you come up with a unique number? Well, at the time this was specified, the people that were standardizing this said, well, if you have a node that has some sort of link layer address, these addresses are usually globally unique. They are a unique number. So why don't we use just the MAC address for the interface ID? We know the prefix. We need a unique number. The link layer address is unique, so let's just concatenate the link layer address to the prefix, and we have a unique address, and that's the problem solved. That is correct to some extent, but obviously, at the time, we are talking more than 20 years ago, the designers overlooked the security and privacy implications of doing this. Let's discuss some of the things. Well, the first one, which I'm noting here, is the correlation of network activity over time. This is very, very simple. If you have an address that is stable and that never changes, and let's say you connect to a server, whenever the server sees that address, it can tell that you are the same guy as before, okay? Simple. You always have the same address, the address didn't change, so it can say, okay, well, this is the same address as before, I can correlate network activity. That, from some point of view, might be bad, but it can actually be worse. Think about this scenario. Let's say that you connect to you're attached to one network, you connect to a server, then you move to a completely different network, you connect to the same server, and now the server can tell that you are the same guy. That's correlating network activity, but across networks. That's way worse. And why is that possible? Well, if you remember that I said that in order to generate Ipv6 addresses, you include your MAC address in the interface ID. The MAC address is a globally unique number. It's like including a serial number. So that means that whenever you are communicating with a public system, you are telling that system what your MAC address is. It's like giving the ID of your node, which is obviously very bad. This could be an example. For example, like first you connect to one server, and you use this address. Then you move to a different network. You employ this other address here. You can see that the prefix is different. The first few bits are different here. But the low order 64 bits, they are the same. Why? Because the MAC address didn't change. Okay? So you move to a different network, your prefix changed, but the interface ID stayed the same. So a server can tell that you are the same guy. Another implication is the use of predictable interface IDs. For example, if you are putting, let's say that you have a big network and all of the systems are manufactured by the same vendor. Obviously, the MAC addresses are going to have like many bits in common. Why? Because many of the bits of the MAC address, the high order 24 bits, are an identifier of the vendor. Okay? So if I know, for example, the MAC address of one system, then in order to guess the MAC address of the different systems, the search space is going to be much smaller. I only need to guess 24 bits as opposed to the 64 or whatever that was. And the last implication is the possibility of an attacker of performing device-specific attacks. The idea is simple. If you're putting your MAC address in the interface ID, somehow you are announcing to the world who is the vendor of your network interface card. So in that case, if for some reason an attacker had a device-specific exploit, it wouldn't even need to do any kind of fingerprinting because just your MAC address is, leaking, if you want, the vendor of your device. So even as soon as the early 90s, if you want, it became clear that this wasn't nice. So all the things were initially, developed and designed like around 1994, 95, and by 1999 already, people started to think more about, security, privacy, and so on, and they say, well, I mean, that of including the MAC address works well, but from a security and privacy point of view, it's not that nice. So the first thing that they tried to do, which is the most obvious thing, is, okay, if I have a system that is behaving as a client, I'm connecting to servers, it would be better if I could change the address like often. Instead of keeping the same address for a long time, just change the address often. It doesn't matter how often, that's a detail. But the idea is like with some frequency, you change your address. How? You just use a random number, okay? So it could be, for example, once a day, you just use a different address. And this is exactly what was standardized in RFC 4941. Sometimes these addresses are called privacy addresses or temporary addresses. For me, the proper name is temporary addresses or just 4941. And the idea is quite simple. in addition to the traditional Slack addresses, the ones that have the MAC address, you also generate these addresses which are temporary and also random. So the ID is a random number that is changed over time. And the idea is simple. Whenever you're going to perform outgoing communications, like behaving as a client, you use the random address. So the address that changes over time. And if your node, for some reason, needs to behave as a server, like receiving incoming connections, then you use the traditional Slack address. Why? Well, because usually when you want to receive incoming connections, you want an address that is stable. Why? Because maybe you post that address in the DNS, and if you are changing the address frequently, you have to update the DNS frequently too. So this would be, we still keep the traditional addresses. We also have the temporary addresses. When we want to communicate with the outside world, we use the temporary one. When we want to receive incoming connections, we use the traditional one. What are the problems with these temporary addresses? Well, first of all, for example, if you look at the standard 4941, it says that if you have, for example, a network interface and you are configuring addresses for multiple prefixes there, well, all addresses are going to use the same interface ID, which is not nice. That means that if you have addresses for different prefixes, the interface ID is going to be the same. So you can correlate activity between the addresses for different prefixes, which is obviously not nice. Another flaw, if you want, in the standard and implementations is that most implementations, what they do, they renew or regenerate the interface ID with some frequency, like, for example, every once a day. Now, if you disconnect to the network and you connect to a different network, they reuse the same interface ID. Whereas what they should be doing is that whenever you disconnect from a network and connect again, you should regenerate the interface ID, okay? But that doesn't happen. As a result of these two things, at least, and a few others, we are working on this document, which is a revision of 4941 to address these problems. Besides these problems, if you want, in the standard and in implementations, there are other things. One is operational problems. If you have ever been the admin of, let's say, an enterprise network or a university network, imagine this. Now you have all of the systems in your network that are changing addresses all the time. So you find a node that was behaving badly, infecting other systems and so on. Somehow you log that, and now when you try to find out what was the system that was doing that, in many cases you don't know. Why? Because they are changing addresses all the time. And from an operational point of view, that's not that nice. Obviously, there are other things. If you have configured ACLs, access control list, obviously if you are changing the addresses all the time, the access control list are not going to work as you would expect. So from an operational point of view, it's not that nice. And there are other things. Like, think about, this would be the most simple example. I was saying that when you configure the temporary addresses, you configure them in addition to the traditional Slack addresses, okay? Now, if the traditional addresses are predictable, for example, like the addresses follow patterns, if I am an attacker and I want to scan a network, I can still scan the network in the same way. Why? Well, the systems are going to have, each system is going to have one random address, which from the point of view of an attacker, I don't care, but they are also going to have an address that is predictable. So from the point of view of an attacker, I just care that there is some address that is easy to find. So these were issues that were not solved by RFC 4941. So as a result of that, and this is the very summarized version of this, in 2014, I published this RFC 7217, which is essentially a replacement for the traditional Slack addresses. I mean, obviously, it's not that simple, but the concept is as simple as this. The idea is that we are going to generate the interface IDs as a result of applying a hash function over a prefix and a secret key, okay? Secret key obviously is secret, and the idea is that if I connect to one network, I obtain one prefix, and obviously the result of this hash function is going to be something. I move to a different network, and of course, since one of these parameters, the prefix, has changed, the interface ID is going to change. So I move from one network to another, the interface ID changed. Now, what happens if I go back to the first network, to the original network? Now, these two parameters are going to be the same one as in the original case. meaning that the interface ID is going to be the same. So what we gain with this algorithm is that you connect to this network, the interface ID is going to be random, some random number, but it's going to be stable. So whenever you connect to this network, you get a random number, but that is always the same. You move to a different network, you get a different random number, but within that network, the number also stays stable. So from an operational point of view, that's nice. The addresses are not predictable, but also they are stable in the different networks. As a side comment, this document was published in 2014. My idea at the time was that the traditional addresses should be replaced with this algorithm. At the time, there was opposition. Things happen. And 3 years later than that, we published a different document, this one, RFC 8064, which essentially says, OK, now everyone, please implement RFC 7217. So that's what sometimes I refer as protocol politics. If you wonder, well, how come that you couldn't just publish this and replace everything? There's no real reason. So we just published the document, the working group didn't agree on that, and three years later, for multiple reasons, the working group agreed that it was time to actually replace what we had. Now you might wonder, okay, well, this is a standard, but what happens in practice? Like if I download some Linux system, I run macOS or something, is this actually implemented? And the answer is yes. So macOS already implements this. If you run anything like, for example, Fedora, I think any current version of Ubuntu, they also implement this. FreeBSD also employs this. So when you are using like any up-to-date or modern operating system, what you find is that the interface ID is going to be a random number, and it's not like they do not include the MAC address anymore. So there was a question somewhere. Yeah.
How do we avoid collisions in the scheme?
So the idea is, and that's a good question. So it's essentially the birthday paradox that you have here. So you have 64 bits, okay? And the idea is that you are not going to have so many systems on the same network that there are going to be collisions. But obviously that can happen. You can just be unlucky. And in this expression, that's why I put these dots here, there's also a value that is a counter. So if you find a collision, you increment the counter so you can select a different number. Obviously, let's say the assumption with this algorithm is that there are not going to be collisions. Why? Because if there are collisions, you might find that the address changes. The address changes, okay? For example, I configure an address, then you run the algorithm for your own system, and there's a collision. So you try a different address, okay? Now let's say that some other day, I'm not connected to the network, you connect to the network, you try the first address, and now it doesn't fail. So you're using a different address. So we did that of including a counter here so you can recover from that possibility, but we hope that you are never going to use it. But the idea is that if for some reason you are so unlucky, well, there's a way to recover from that. The addresses are not going to be stable, but at least it's going to work as opposed to just break, okay? There are a few more details here, obviously. For example, in this expression, you only have the prefix and the secret key. There are obviously more parameters there because you could say, okay, what happens if I have, let's say, a system with two different network interface cards, two different cards? Well, based on this algorithm, if I connect two cards to the same network, they both get the same address, okay? Because the parameters are the same. Well, in the real algorithm, you also include an interface ID, something that differentiates between the different network interfaces. But let's say then the most important part of the concept is that you have a prefix and the secret key. If you look into the RFC, obviously there are all those details, like well, what happens if there are collisions and so on. That's why the document is like maybe, I don't know how many pages, maybe 20, as opposed to just 2 or 3. So this has replaced already the traditional Slack addresses. So you might wonder, well, so now we have replaced all those predictable addresses with these addresses that are random. So from the point of view of an attacker or a guy that does security and is doing penetration tests, well, is that the end of network reconnaissance? Like now I cannot scan systems anymore? Well, what I might say is that you are not going to be able to do brute force address scans, obviously. Now, the addresses are going to be random in a search space that is very big. So if you just want to do things in the same way as in the IPv4 world, no, it's not going to work. But there are many things that you can do to actually discover systems. We actually wrote an entire RFC, 7707, which is all about network reconnaissance in IPv6. Different techniques that you can employ to actually discover systems. As a kind of like summary, so that if you say, okay, I don't want to go through the RFC, but just give me some ideas of what I could use. For example, it's possible to do smart address scans for some addresses that follow patterns. There is this tool that I produce, Scan6, which is a tool that analyzes the pattern of the address and tries to reduce the search space. I mean, I'm not going to cover the tool in detail, but the tool is publicly available. It has a manual page, so you can give it a try. It's possible to do DNS Reverse Enumeration. Again, this employs the DNS reverse mappings. It can be employed to find systems. It's also possible to find to use search engines. There's these scripts that I implemented in my toolkit to be able to leverage search engines. And it's also to leverage something called certificate transparency, which is kind of like, without getting into the details, like a repository where you have the logs of all of the certificates that have been publicly posted. So if you want to find systems, for example, either for a whole zone, like .ru or whatever that is, or for some specific site, you can use many of these tools. So this is one of the tools, Scan6. If you run the tool against some domain, the tool will automatically reduce the search space. And the tool is also able to do host tracking. I was saying, when I discussed the security implications, I said that it's possible, if you're using traditional Slack addresses, to track a node, like correlate network activity. So what the tool is doing here, without getting into details, let's say that I know that his system has some specific MAC address, okay? And I know that today he could be at this conference, at the office, or at home. And I know that the IPv6 prefix for the conference, for example, is this one, the prefix at his home is this one, and the office is some other one. Well, you give the tool his MAC address and the multiple prefixes, and what the tool does is obtain the tool puts the prefix with the MAC address and tries to find if there's something there. And it tries in all the combinations. And obviously, if he's employing traditional Slack addresses and he's connected to one of these networks, I'm going to find out in which network he is. Obviously, this is assuming that he's employing traditional Slack addresses. So some comments on IPv6 extensions. Essentially, this is the format of an IPv6 packet. In IPv4, you have a variable length header in which you can put options, extensions if you want. And in the case of IPv6, the structure of the packet looks a little bit like this. So you have a fixed IPv6 header. This is the payload. And if you want to put options, well, the options are included in what's called extension headers, okay? So they are not there, but if you want the options, you have to insert those extension headers over there. If you look at the fixed header, it says, okay, the next header is of type 60, which is destination options. So I process this one, I jump here, and then it says, okay, the next header is 06, which is TCP. So I jump to the next one. This is like a linked list, okay? If you did computer science, it means that if you want to get to the last node, in this case, the payload, the TCP segment, you have to start from the first node and process all the nodes till you get to the last one, okay? What are some problems or some details with extension headers? Well, first of all, the standards are flexible or maybe even too flexible, meaning that they allow, for example, that a packet can have multiple extension headers of the same type. This is an example of that. So fixed header, destination option header, and another destination option header, and then the payload. Now you might wonder, well, why would I ever include two copies of the same thing? Well, there's no really use case for that, but the standard allows for that. I mean, like everything, when you allow this kind of thing, it increases complexity, and complexity is the enemy of anything, of everything, including security. There are other things. This is, maybe it's even harder to grasp. Let's say that within the system, you generate this packet, okay? But you don't send it on the wire. You're just generating the packet in your local system. It's a fixed header, destination options, and then the payload, okay? You can actually, before you send that, you can actually fragment that packet into 2 pieces. And what you do in this case, you include part of the extension header in the first fragment, and then the rest, which means the other part of the extension header and the payload, in the second. Okay? So first fragment here, second fragment here. If you look at the first fragment, that's crazy. Why? Because the first fragment doesn't even have a piece of the payload. It just has, it only has like a piece of the extensions. I mean, there's no real use for that, but the standard allows for that. Okay? Or at the point, it was allowing for that. This is like crazy, problematic for so many reasons, but you know, the standard allows for that. You might wonder, okay, what are the problems, you know, with these extension headers? There are many problems. First of all, and this is not even security, there are operational problems. There are boxes, for example, like load balancers, that usually they have to be able to look at the layer 4 packet, like for example, the TCP ports, okay? Now, if you have a packet that is fragmented in the way that I just described, for example, if I go to the previous packet, this one, the first fragment doesn't even contain the transport protocol header here. It only has a piece of the extensions. So if these packets were to hit a load balancer, the load balancer wouldn't know what to do with that. And that's problematic from an operational point of view, not even security. But obviously, there are security implications of these two. First of all, you know, complexity usually leads to the ability of evade security controls. Why? The attacker can produce packets that are so complex that then if you have, for example, a network intrusion detection system, well, it's not that smart to actually put the packets all together to actually figure out what's inside. There are other things. For example, it's possible to do denial of service as a result of the processing requirements. And let me give you a very concrete example. There are some devices that if they have to process packets like these ones, you know, with extension headers, instead of doing the processing in hardware, they have to resort to CPU processing. So you send a normal packet, these devices can process the packet in hardware, so things go very fast. Now, if you send packets with extension headers, they are not able to process the packet in hardware, so they have to do it in software. Obviously, the performance of that is like extremely bad, and if an attacker were to send like many packets like this, obviously the performance of the system goes down. Obviously, this is not a problem if you are just thinking about your, your home router. It doesn't matter. But if you think about a router that might be employed by your ISP, obviously they couldn't deal with a large flow of packets that have to be processed in software. There's also like denial of service attacks, which don't really have to do with the specification itself, but with implementation errors. Like whenever you have things that are kind of like hard to process, there's always some implementation that does the processing wrong. And there have been many cases already of vulnerabilities, kind of like ping of death, based on the processing of extension headers. They just do the processing very badly. And finally, there are issues that have to do with specific extension headers. Just to give you an idea, when Ipv6 was first specified, they specify a routing header similar to the source routing that we had in the IPv4 wall, with similar consequences, denial of service and so on. What are what's the work that has been done in this area? This is stuff that has been done like in the last 5–10 years. First of all, first document here, RFC 7112, it prohibits this case that I mentioned here, okay? So now it is forbidden to generate this kind of packet. Whenever you produce a packet, the packet has to contain all the headers, IPv6, extensions, and upper layers. What else? These two, 6946 and 8021, have to do with details that we are not going to cover. there is this other RFC, which is not the standard, but is quite useful, which is 7872, and it boils down to this. If you look at some of the research that has been done in IPv6, like in the last 5 years, there is a lot that has to do with extension headers. And you will see that people say, well, if I use extension headers, I can evade, whether that's suricata, snort, or whatever that is. Now, a problem that you find in the real world is that if you send packets with extension headers into the public internet, there is a very big chance that your packets are dropped, up to something like 20 to 40%. And what does that mean? Well, on one hand, it means that, using extension headers is not that nice for attacking purposes. Why? Because if you try to attack a system using extension headers, well, that means that it's very likely that your packets are going to be dropped. But there are other implications too, even from the defensive perspective. You might have heard about Ipsec, which is obviously about doing encryption and authentication at the IP layer. In the case of IPv6, Ipsec employs extension headers. Okay, so Ipsec is an extension header. What's the problem with this? Well, Ipsec packets are also dropped in the public internet. So if you want to do, for example, an Ipsec tunnel between two, let's say, two faculties of a university, chances are that your packets are going to be dropped. So you will have to do something else. It's an SSL VPN, whatever that is, but it's quite likely that Ipsec is going to fail. And finally, which is this last RFC, a few months ago, the core IPv6 standard was revised. So the original IPv6 standard was RFC 2460, and that RFC was revised. So now the IPv6 standard is 8200. And this RFC now incorporates many of the things that I discussed before. So when you compare the current v6 standard, well, in that standard there were many things that were improved. Like many of the patches that I discussed before have been incorporated. Tools. Well, there are many tools for playing with extension headers. Two of the tools that I specifically mentioned here is Path6 and Blackhole6. Path6 is essentially a traceroute tool with support for extension headers. So if you want to test, for example, is it possible to get to some specific network using this or that extension header, you can use this tool Path6. And then you can check, well, if it would actually make sense to try, for example, to do the pen test or the attack using extension headers or not. This other tool, Blackhole6, is more of a troubleshooting tool that essentially tries to tell you where exactly in the network the packets with extension headers are being dropped. Some comments on address resolution. Address resolution is obviously mapping an IPv6 address into a link layer address. If you want to use your IPv4 knowledge, that's like what ARP does in IPv4. In IPv6, it's essentially the same thing, but just more complex. So instead of doing, ARP, like in before, which are like very simple packets, in IPv6, the packets that are employed for address resolution are IPv6 packets, meaning that they can use extensions, they can be fragmented, and so on. Think about, just for a second, think about the possibility of ARP traffic now being fragmented and so on. So what was very simple now became much more complex, okay? What are the attacks that are possible for address resolution? Obviously, the same as for IPv4. Like in the case of before, you had the ARP cache poisoning. You have something similar in IPv6. It's just that the packets are different. You might wonder, well, what are the possible countermeasures? Well, essentially, there are two things. The first one is something similar to what you have in IPv4, which is either traffic monitoring or policing, meaning monitoring means that you're not going to prevent the attack, but you might be able to detect that the attack is happening. Let's say it could be something like ARP watch in IPv4, something similar to that. Traffic policing is obviously try to filter packets in a way. And there's something interesting that is, let's say, new for IPv6, which is called secure neighbor discovery, okay? So let's discuss these two a little bit. When it comes to monitoring or policing neighbor discovery traffic, this ARP for IPv6, things are more complex. Why? Because the packets are more complex, the traffic is more complex. So in theory, this traffic now can have extensions, can be fragmented, and so on. So that means that the attacker can make things way more complex for you, the guy that is trying to defend the network. In particular, if he's able to fragment the packet, that things get much more tricky. The other thing is SEN. Essentially, I mean, SEN is complex, or kind of like complex. Essentially, what it does, by means of cryptography, it allows nodes to prove that they own a specific address. They allow a host to prove that they own an address. And SEN also allows routers to be authorized. Like, you can somehow tell that, what the node that you are communicating with is a real router. Without getting into the details, and in order to save you some time, the idea is simple. SEN, first of all, is hard to deploy, requires a PKI, and usually dealing with a PKI just to secure ARP doesn't make much sense. And even if you were that crazy, even if you try to do that, well, SEN is not widely implemented. Just to give you an example, Windows doesn't ship with an implementation of SEN, meaning even if you want to do it, you cannot secure Windows systems with SEN. I also think that there are probably many other things on which to to use your time and your resources rather than SEN itself. Another thing to comment, which is a side comment. If we try to compare ARP with neighbor discovery, okay? In the case of ARP, the ARP cache, which is the list of address and MAC address, usually is limited. Why? Because in a typical IPv4 network, you don't have more than, let's say, 256 systems. Because of the size of the network itself, there's like an artificial limit that is there. So no matter what you do, because of the size of the network, usually the number of entries are not going to be more than 256. Now, what happens with IPv6? Well, the networks are /64. So that's like many possible different nodes. And what happens? Well, many implementations are very stupid, if you want, in that they don't enforce limits on the size of the cache. So what's the IPv6 version of the ARP cache can just grow and grow and grow and grow. Like in some systems, you can consume all the system memory just on the neighbor discovery cache, okay? That's an implementation problem, if you want. There's some work that has been done in this area. This RFC 7980 prohibits the use of fragmentation for neighbor discovery traffic, so now things are a little bit more sensible. And these other two documents, they have to do with mitigating attacks against the neighbor cache, to try to prevent the neighbor cache from growing too much. Tools, well, there are in most of the popular toolkits for IPv6, you have tools for playing with neighbor discovery. In the toolkit that I produce is NS6 and NA6, but this other toolkit, THC IPv6, it also has tools for that. Next topic is auto-configuration. As I said before, auto-configuration in theory is simple in IPv6. You connect to the network, you ask the network parameters, among others, like for example, what's the prefix that you should use? You configure your addresses and you might configure other parameters. As you might expect, there are vulnerabilities that are associated with this. Usually it's the same kind of stuff that might happen in IPv4, with only you could say an important difference is that in the case of IPv4, typically, you connect to the network and there is a very small window during which you are obtaining network configuration and you can be subject to an attack. Whereas in the case of IPv6, you might connect to the network, you configure your own system, but at any time, the router can send you updates when it comes to network configuration. So you just configure, maybe even if your system has already been completely configured, I connect to the network 1 hour later and I can still attack your box. What you can do, obviously, same kind of thing as in IPv4, denial of service, man in the middle, and all of that. Mitigations, well, there's secure neighbor discovery, which is what I explained before. SEN can be employed for address resolution and also for auto-configuration, but I already told you that, in practice it's not useful. And there is a technique called, for packet filtering that is called router advertisement guard. If you have some experience in IPv4 network operations, you might know something that is called the Hcp Snooping. The idea is simple. You have a switch, and you say, OK, I have many ports in my switch, and I know that the DHCP server is going to be connected only on this port. So I will only allow DHCP server packets on this port. If any other system tries to pretend to be a DHCP server, I just block the packets. Well, router RA guard is exactly the same, but for IPv6. The concept is the same. So you say, only on this port, I will allow the RA packets, the server, the router packets, and on all the other ports, I will drop and filter those packets. What happens is that, again, if you use fragmentation, extension headers, and so on, you can easily circumvent these devices. I have been to networks that have like literally thousands of clients, and thousands of clients connected to the same network at layer 2. It's not that nice. And I asked the guys, like, what are you doing for security? Because any system could just screw up anybody else. We're doing RA guard. Well, yeah, in theory, but in practice, an attacker can just spoof a packet, use fragmentation or extension headers, and you completely circumvent router advertisement guard. These are two RFCs that have been published on the topic. First one, essentially, is what I mentioned before, prohibit the use of fragmentation for, in this case, for auto-configuration. Second one, it discusses RA guard evasion, and it also provides advice to vendors that are implementing RA guard. Tools, these are the tools in my toolkit, and there are also multiple tools on this other toolkit, THC. The last topic that I'm going to talk about, just very briefly, is the security implications of B6 on IPv4 networks. And you might wonder, well, this doesn't make any sense, because B6 and B4 are different protocols. So what can be the implication of B6 on B4? Well, if you look at any IPv4 network, well, it already has support for IPv6. Probably any system that you might be using right now has an IPv6 implementation that is enabled. So that means that even if you think that you have an IPv4 only network, well, it does have support for IPv6. Maybe you are just not using it. And there is there are many examples that I could provide, but this is something that is interesting. Even if you don't care about B6, it's kind of like interesting. Let's assume that you come to a conference such as this one. So you assume that there's going to be lots of people trying to sniff your traffic, stealing passwords and all of that. And you say, well, I'm going to try to prevent that, and I'm going to use a VPN, okay? There are many VPN implementations that they only support IPv4. So if you send IPv4 packets, yeah, they tunnel the IPv4 traffic, they encrypt the IPv4 traffic, and you send it to the other endpoint, whatever that is. But they do nothing about IPv6. So what could I do as an attacker? Well, I intentionally enable B6 on the network. And now when you try to communicate to some system, if you happen to use IPv6, and since your VPN doesn't know anything about IPv6, now all your traffic goes in the clear on the local network. So this means that even if you don't care about IPv6, you should be conscious about it. Why? Because there could be situations in which you think you are not going to use it, or you are not using it, and it's even worse than that. So you assume that all your traffic is being encrypted and protected because it's going on an IPv4 tunnel, and because of IPv6, it happens that it's going in the clear. In my particular case, I just found it by chance. I was once using a VPN client, I was sniffing my own traffic, and I said, what's going on that all of this is going in the clear? Well, I was using IPv6. There are cases in which it could be an attacker actually, doing that on purpose, like maybe this network doesn't support IPv6, and an attacker could intentionally enable IPv6. But it can also happen that if you connect to a network that, it just implements B6, and your VPN client doesn't support it, well, even without knowing, and not because there is some attacker doing that on purpose, maybe you are sending your traffic in the clear. My short advice on this is that if you think that you are not using IPv6 or you don't want to do it, make sure that that is the case. For example, what I used to do for VPN, when I was going to use the VPN, I was completely disabling IPv6, so I knew that my box was only communicating with before. work in this area, there are two RFCs that have been published essentially on this topic. First one, 7123, is specifically about many attacks that have to do with the implications of B6 on B4 networks. And the second one is about the specific example that I mentioned about VPN leakages. It's actually complex, or actually it's complex to fix it. So if you are interested, I suggest that you read this RFC, because I didn't do like a lot of research in the area, but it's quite likely that even if your VPN does support IPv6, it is still possible for an attacker to trigger a traffic leakage so that the traffic goes outside of the VPN. Conclusions. First of all, there are many improvements with IPv6 that happened recently. If you look at all of these patches that I discussed, all of them happened in the last 5 or 10 years, which is quite recently. If you look at implementations, at least the open source one have generally catch up. So it means that all of these RFCs that I have discussed, they are implemented already. But I would say that we still need awareness about IPv6 security. There's even ISPs that they get to deploy IPv6, but when they ask them, well, what do you do in terms of security? No idea. At the end of the day, my advice is that, whether you like it or not, you will end up deploying B6, so it's time to experiment with it. Read a book, build a virtual network, whatever that is, but start playing with it, because sooner or later you will have to deploy it in production networks. I don't know if there are any questions. Yeah.
I have a small question, please. If I'm implementing a firewall and I want to detect an IPv6 nmap scan, I can force nmap to IPv6. Is it possible to detect it without false positives? Because if I remember, broadcasting IPv6 is the exact...
What kind of attack you are trying to...
Not an attack, a scan. Like I'm an attacker and I want to map with the IPv6 the network.
It's possible, but a problem that you have when it comes to... a problem that you find when it comes to security devices is that there's like a lack of parity of features between B4 and B6. What does that mean? That maybe you have a firewall that on IPv4 it can do all of these things, and when you look at what that firewall is able to do in IPv6, not that much. So it might be that you can do it, not because it's not possible to do it in IPv6, but because this IPv6 support is limited. And there is another thing that at times, there are devices that in theory have support for both protocols, but they support, for example, IPv4 in hardware, but they support B6 in software. So in theory, you can use it, but if you are trying to use that device in a real network, you cannot rely on software processing. So it's tricky. I don't know if there are any questions. There's no more time, I guess. Only one more question.
Only one.
I think that's it. Anyway, that's my email address. If you have any questions, feel free to drop me an email or just talk to me during the conference. And we have an IPv6 hackers mailing list that's in English. That's where most of the people that are doing B6 research or standardization are subscribed to. So if you have a question, you don't need to rely on my own perspective, but actually post it there so you will get perspective from many people. So thank you.
Thank you.